Well, thank you, of course, for the invitation. So the plan is to give an overview talk about radical rings, braces, and how those objects interplay with the Yang-Baxter equation. So I will try to keep this, as elementary as possible. So, what is wrong here? Sorry. I don't know what it's. I cannot change this. Okay, yes, first. So the problem I want to start, try to solve somehow is to study set theoretic solutions to the Yang-Baxter equation. So what is that? Well, the problem was formulated by Drinfeld in the 90s. And well, the idea is to try to find pairs, XR, where X is a set and R is a bijective map that satisfies the Yang-Baxter equation, which is this equation that we have here, okay? So the first works are those of Gateva, Ivanova, and Vandenberg, Etingov, Shedler, and Soloviev, and also Gateva, Ivanova, and Majid. So the idea in all these papers was to use like some sort of algebraic object to try to understand this problem. So for example, in the paper of Gateva, Ivanova, and Vandenberg, they were using some sort of ring theoretical combinatorial structure, which is known as group of I-type. I think Goff, Shedler, and Soloviev were using group cohomology, and in particular bijective Wanko cycles, and Gateva, Ivanova, and Majid used, for example, a matched pair of groups or matched pair of semigroups or things like that. So what I want to try to do here is to try to use this sort of generalization, simultaneous generalization of groups and rings, which we know as braces. So let me first give you some examples of solutions. So the flip is going to be the trivial solution for us. So it is just, this map, the only thing that this map does is to switch X and Y. Then we have this other family of solutions, which is known as permutation solutions or Lyubashenko solutions. Anastasia discussed this family of solutions. So the idea is that you take two permutations, two bijective maps that commute with each other, and then you produce this solution that you have here. And these are quite important, okay? And if you have a little bit more of structure over your set X, then you can do more stuff. For example, if X is the set of integers mod n, then you can produce, for example, either this solution, the first one that I wrote here, this, this, or the other one, okay? So the idea is that one, right? If you have a set with a little bit more of a structure, then you can do more stuff. So what if we take, for example, X as a group? Then, well, you see, we have these two very interesting solutions. So the first one essentially says that conjugation will give you a solution. And the other one is a little bit funny, right? This was first found in a paper of Wada concerning representations of the braid group. So here I have to mention something which I find quite amazing. So if you do X times Y here, it's the same. So you get X times Y. And if you do this guy times this guy, again, you get X times Y. And the same happens here, right? So if you multiply X times Y, and you multiply this first coordinate by the second coordinate, again, you get X times Y. So, of course, this is not an accident. It means that there is some sort of symmetry that you can try to understand, right? Of course, maybe X is just a set, it is not a group, so it has no multiplication, so what can we do? Well, this is most of the whole point of my talk, okay? So, to motivate my talk, I will like to start with this concrete problem. What I want to do is to try to construct finite set theoretic solutions. What does it mean? Well, I don't want to be very precise here. It could be, for example, constructing solutions up to isomorphism using computers, or just produce a huge family of solutions, or whatever you want, right? But this is typical way of, at least my typical way of approaching some new topic. I try to construct, if not all, most of, say low size objects, okay? but I need to put this in context. And well, the context is going to be combinatorial, which means that I need some groups acting. That's why you consider non-degenerate solutions, right? So non-degenerate solutions are those solutions that you can write like this. So you can always write the first coordinate as I did here and the second coordinate as I did there. But I'm going to ask that all the maps, sigma and all the taus are bijective maps, okay? These are non-degenerate solutions. Of course, if you have a non-degenerate solution, then you have different groups acting on the set X, right? Like the group generated by the, say, the sigmas, or the group generated by the taus, or maybe the group generated by the sigmas and the taus and everything. So this is going to be the set, okay? And so the point is that this was a very interesting observation by Rump. If you consider if you take a radical ring, then you can produce solutions. So radical rings produce solutions. How does it work? Well, first of all, take any ring you want. You can define the Jacobson circle operation like this. And it turns out that this operation is always associative with neutral element equals to 0, right? So we are going to say that R is a radical ring if and only if, well, R with this new operation, this circle operation, is a group, okay? So radical rings are quite important in non-commutative ring theory, but quite funny for some of you, right? Because they are rings without a one, which, well, they look like very different from the objects we are used to work with, but they are not so fun, right? If you take any ring you want and you compute its Jacobson radical, then this Jacobson radical is an example of a radical ring. So it's not so funny as you might think at the beginning. And here you have a very concrete example of a radical ring, right? This set with the usual operations is a radical ring. And as I said, Rump proved that radical rings produce solutions. So he gave a very, very explicit map, very explicit description of the solution you can produce with a radical ring. So you see, I wrote this using only the addition of the ring and the circle operation. And then, of course, I need to use that indeed I have a radical ring. I need to use the inverse of an element with respect to the circle operation. This is the prime that you see in the second coordinate, okay? So with this expression, you produce a non-degenerate involutive solution to the Yang-Baxter equation every time you have a radical ring. So here, of course, you see something, right? So you have a very concrete expression using addition and circle operation, and then you know that with this crazy formula, you get a solution, right? So do you really need a radical ring to produce a solution with such a crazy formula? And the answer is no, right? So this is how you get the definition of a skew brace. So a skew brace is going to be a triple. So you have a set A, you have an addition, and you have a circle operations. These are binary operation on A, of course. And in such a way that A with plus is a group, A with a circle operation is also a group. Maybe not, I mean, the additive group is maybe not commutative, okay? But it doesn't matter. I use this notation because I want to, you know, keep track of ring theoretical ideas. And then you have, of course, a compatibility condition between these two structures, which is this sort of crazy distributivity, okay? So this definition of a skew brace, which says that, okay, I have a set with these two operations, and then I have this very symmetric distributivity somehow, is motivated by the work of Sedot, Jesper, and Odninsky, right? Because the original definition of a brace given by Rump, which was only useful to deal with involutive solutions, was somehow different, okay? But Sedot, Jesper, and Odninsky reformulated this in better terms, and using this, it is somehow very natural to go to this general structure, okay? Okay, examples of braces, because of course you need examples, right? So the first example, or the first family of examples, is radical rings. So this is I mean, it's quite interesting, right? Because radical rings are examples of skew braces. So the theory is non-empty and quite interesting at least from ring theoretical point of view. Of course, you can also have group theory somehow as the trivial case, right? Because if you have a group, then you can turn this group into a trivial skew brace. Just, the circle and the addition are the same operation. And also, Majid mentioned this. So if you have a group with for example, a group with an exact factorization, meaning that G can be every element of G can be decomposed in a unique way as an element of a subgroup A and a subgroup B, then you can turn this information into a skew brace with this circle operation. Okay, so you see that here you have like three different families of examples, highly non-trivial examples of skew braces. So why you care about skew braces? Of course, skew braces produce solutions, and the theorem is essentially the same theorem that Rump proved, right? So if you have a skew brace, then you use the same crazy formula that Rump found for radical rings, and then you get a non-degenerate solution. And moreover, the solution is involutive if and only if the additive group is abelian. So this is the case considered by Rump. Okay, and you can go further. I mean, because it's not only that skew braces produce solutions, but it's more than that. It's like skew braces produce somehow universal solutions, right? All solutions are some sort of restrictions of solutions coming from skew braces. To make this precise, well, I need to recall the definition of the structure group of a solution, which was first considered by Etingov, Shedler, and Soloviev, which essentially, keeps track of this idea that I mentioned at the beginning, right? This invariance property. Just to say, like, X times Y is the same as U times V, right? So you consider the group generated by X with those relations, and then, so over this group, you have a unique brace structure in such a way that your arbitrary non-degenerate solution is some sort of restriction of the solution associated to the brace that you have over this group. Of course, since solutions are arbitrary here, well, this restriction is a little bit more technical, right? It is not a restriction in the strong sense somehow. You need to use some map that puts X inside, in some sense, the structure group. But of course, you have to be careful here, but because this map iota, it might be not injective, right? In general, it is going to be injective in the case of involutive solutions, but not in general. So this was proved in a paper with Agata Smoktunovics, and also in some sense in the paper with Guarnieri, which was my student, my master's student. But you can go even further, right? Because you can prove the following. So skew braces are some, as I said before, right? They are some sort of universal when you want to recover all solutions, right? So if you have a non-degenerate solution and you have any brace and a map from X into a brace B, which is somehow a morphism of solutions, where in X, of course, you consider the solution which is given, and on B, this canonical solution that you have because B is a skew brace, then there exists a unique homomorphism, brace homomorphism, from the structure brace to B, such that, well, you have this natural property, okay? And this is quite important because in some sense, this is telling you that if you want to study solutions, then you need to study braces, right? In some sense, you will be able to translate almost all properties about braces into properties, combinatorial properties about solutions, if you know what to look for, okay? And similar results were known in the literature, for example, in the work of Etingov, Shedler, and Soloviev. Of course, Rump did this for involutive solutions, Soloviev also for arbitrary solutions, Lu, Yan, and Zhu also. I mean, this sort of idea was there before we did this, right? We just used the language of braces, which I think it is quite convenient. So but the point is that braces are quite interesting. And we in the morning we were in two talks about Hofgalois extensions, and they were talking about the holomorph and why braces and Hofgalois extensions are somehow related. The idea is that, well, braces are in correspondence with regular subgroups of some construction, right? And I want to recall this because this is quite useful also for the theory of the Yang-Baxter equation. So you start with a group, additive group, so the operation is plus, maybe not commutative. Then you consider the holomorph of your group A, which is this particular semi-direct product. Of course, here the action is the natural action of the automorphism group on A, and well, you say that a subgroup of the holomorph acts on A with this formula, and you say that a group G, a subgroup G of the holomorph is regular if, of course, this action is regular, right? So every time you take two elements in A and B, there exists a unique element in G connecting these two, okay? And the point is that, well, so first of all, if you have a regular subgroup of the holomorph, then you have a bijective map. And if you have a skew brace, then you can somehow realize your skew brace as a regular subgroup of the holomorph. And somehow this construction is very general, right? So if you have a skew brace, then you can realize your skew brace as a regular subgroup of the holomorph, and conversely, if you have a regular subgroup of the holomorph, then you have a skew brace, right? So every time you have a regular subgroup of the holomorph, then you have a skew brace with this operation. A circle B is A plus F of B, where F is, of course, obtained using this bijective map that I mentioned before. So this sort of correspondence between skew braces and regular subgroups, of course, was there before. You can find some ideas in this paper of Caranti, Childs, and this other guy that I don't know if I will be able to pronounce correctly. Also in the work of Catino and Rizzo, and also in a paper of Achicher in the case of involutive solutions, okay? So again, some ideas were there, but with braces or with skew braces, you can just put all them together somehow. And okay, so you can use this correspondence between skew braces and regular subgroups of the holomorph to construct a huge database of finite skew braces. Maybe up to size, I don't remember exactly, but up to size 200 maybe, or a little bit more, with some exceptions, right? Like 64, size 64, or size, I don't know, 128. If you have big prime powers, then it is a little bit more complicated. And this algorithm that I did with Guarnieri was improved recently, and with this you can go even further, right? But still, big powers of 2 are a problem. And of course, as we know from what we did in the morning, because of this connection that you have between skew braces and regular subgroups, is that you can use somehow the theory of skew braces or all the ideas, you know, around skew braces to study Hofgalois extensions, right? Because, well, regular subgroups of the holomorph are also quite important in the theory of Hofgalois extensions. So just this terminology that I have here comes from Hofgalois. So if you have a property of groups, say X, I will say that a skew brace A is of type X if the additive group of the skew brace belongs to the class X. So for example, skew braces of abelian type are those braces where the additive group is abelian. And this is essentially what you need if you want to study involutive solutions. And skew braces of nilpotent type are those braces or skew braces where the additive group is nilpotent. This is some sort of natural generalization of these braces of abelian type, which are the braces studied by Rump in connection with involutive solutions to the Yang-Baxter equation. So let me mention some open problems on skew braces. Okay, so the first one appears in the theory of Hoffa-Lois extensions. So the idea is somehow easy, right? So you have a skew brace, which means that you have a set with two groups structures, and then you want to see how these two structures are connected, okay? So the first problem is the following. Suppose that you have a finite skew brace and the additive group is solvable. Is it true that the multiplicative group is solvable? Well, this is still open. We don't know the answer, and it seems to be quite hard, okay? You can also find this problem in this famous notebook of problems, group theoretical problems. It was formulated by Biot, this problem, and there are some cases where you can say something, like for example, in the case of infinite braces, or maybe if your brace is a radical ring, then you know the answer, but in general, it is not clear at all. It is quite hard. Very good. So, as I said, of course, you can also formulate similar questions, right? So you want to see how these two groups that define the skew brace interact, right? So, for example, a well-known result of Etinghoff, Schedler, and Sadoviev says that if you have a finite brace of abelian type, then the multiplicative group is solvable. You can, of course, just somehow use the same technique to extend this result to skew braces of nilpotent type. So if you have a skew brace, finite skew brace, and the additive group of the skew brace is nilpotent, then the multiplicative group of the skew brace is going to be solvable, okay? Okay, see, this was also a conjecture of Biot. Again, the problem appeared at the beginning in the theory of Hoffa-Lois extensions. So, but of course I will mention this in the language of braces. So suppose that you have a finite skew brace A. If the multiplicative group is nilpotent, then the additive group is solvable. This was recently proved by Zhang and King. And I can give you the proof because it's quite short. I would not say it is easy, but it is quite short. So let's say that K is the additive group and G is the multiplicative group. So you are going to consider this map, which is, you remember, this is the map that we used to realize a skew brace as a regular subgroup of the holomorph. So again, this idea is behind, right? So you consider this map, this lambda is a lambda map of a brace. So this map is a group homomorphism. So G is nilpotent, so it means that lambda G and f of G are also nilpotent. So then you can consider this semi-direct product of the additive group and the lambda, which is a group that has this factorization as f of G times lambda G. So it is a group that can be written as a product of two nilpotent groups, and it is finite. But then a very famous theorem of Kegel and Wieland implies that this semi-direct product is going to be solvable. And of course, if this semi-direct product is solvable, then K is going to be solvable because it is a subgroup of the semi-direct product, okay? So in some sense, this result is a consequence of this quite deep theorem in group theory or in group factorization theory, okay? But it is not, I mean, it is not that you can do something like this to prove Biot conjecture. This I don't know how to do that. And well, you don't have a theorem like this that you can apply in the other setting. And with the same idea, you can prove other results. So for example, you can prove that if A is a finite skew brace in such a way that the multiplicative group is abelian, then the additive group is meta-abelian. This is a famous theorem of Ito, somehow applied into this setting using exactly the same idea as I gave you before. And also, if the multiplicative group is cyclic, then the additive group is super solvable. Okay, again, same idea, using this realization of the skew brace as a regular subgroup of the holomorph, and then using a group theoretical result on factorization. This was the first problem. So another problem is the following. So we are going to say that a finite group G is a involutive Yang-Baxter group if it is isomorphic to the multiplicative group of a skew brace of abelian type. Okay, so maybe it looks a little bit funny, this terminology, but somehow what you want to understand is which groups can appear as the multiplicative group of a brace, of a skew brace. But in order to make the problem somehow more interesting and challenging, well, you just consider braces of nilpotent type or even of abelian type, okay? Good. So, as I said before, right, this theorem of Etingov, Shedler, and Soloviev, involutive Yang-Baxter groups are always solvable, right? So, natural question is, which solvable groups are involutive Yang-Baxter groups? This is, of course, we don't know the answer, okay? This is wide open. It's quite difficult to answer this question. What we do know is that, well, not every solvable group is going to be an involutive Yang-Baxter group. This was somehow done by Rump, but without details, and David Bachicher found a proof, right? A complete proof. However, what I would like to understand is which is the minimal, for example, the minimal example of a solvable group that it is not an involutive Yang-Baxter group. Because this construction of David is quite difficult. It uses Lie algebras and also some computer calculations. And I don't remember the size of the counterexample, but it is quite big, right? I think it is maybe a group of order P to the 7 at least, and P is at least 11 maybe, I don't know, but it is huge. I would really like to have a very small concrete example, and I don't know where to find this. And a related problem is the following, which was formulated by Sedot, Jesper, and Odninsky. So say that I take a nilpotent group of class 2. So is this nilpotent group the multiplicative group of a skew brace of abelian type? Again, we don't know the answer to this one, okay? And of course, there are some variations, right? I mean, for example, you can try this to find when this nilpotent group of class 2 is the multiplicative group of a radical ring, or you know, some variations like natural variations, which are all of them quite hard. Very good. Okay, what is wrong here? Good. And also, this is a very related problem. It was formulated by Rump. So is there an example of a non-involutive Yang-Baxter group where all CELO subgroups are involutive Yang-Baxter? Again, this is quite far to be solved. I really have no idea about how to attack this. It seems to be very, very difficult. Okay. Okay, but let's go back to skew braces, radical rings, and solutions, right? So you remember, so we found the idea or the definition of a skew brace just trying to, you know, imitate what you get from radical rings, right? So this means that you can use, in some sense, ideas from radical rings to study solutions, right? But on the other hand, skew braces are some sort of generalization of groups, right? So again, you can use ideas from groups to study solutions. And this is what we want to do. So let's concentrate on involutive solutions because it will be easier, right? So involutive solutions are those solutions such that the square of R is the identity, right? So the funny thing here is that, well, if the square of R is the identity, then you don't need to know a lot about it. You don't need all the sigmas and all the taus, right? You only need half of them because, well, you have these two equations that I wrote there. So you can, for example, find an expression for all the taus using only the sigmas, okay? Moreover, if you have an involutive solution, then this map T that I wrote there is always bijective and you can conjugate sigma x, each sigma x by this map T in order to get all the taus, right? And moreover, the group generated, this group that acts on X, the group generated by the sigmas and the group generated by the taus are isomorphic, but not only as groups, but are isomorphic as permutation groups on X, right? So for involutive solutions, well, things are a little bit easier. And so if you go to the list of solutions, you just study the huge database of solutions that you have, you recognize some patterns. What you see is that almost all solutions, really almost all of them, have a very particular form. So they are sort of extensions, if you allow me to say this in that way, they are sort of extensions of trivial solutions. So they are generalizations of permutation solutions. So let me explain that. So you start with a non-degenerate involutive solution written like this, and we are going to define an equivalence relation on X given by this. X is equivalent to Y if and only if sigma of X is the same as sigma of Y. So it is easy to prove that this is an equivalence relation, but what it is interesting is that if you quotient out X by the relation, then you still get a solution. You still get a non-degenerate involutive solution. And this new solution is known as the retraction of X, right? And if you go to the list of solutions, then you realize that almost all of them can be retracted into a solution of size 1. This means that, so you start with a solution, and then you quotient out by the equivalence relation, and you get something smaller, and then you do this again, and then you get something even smaller, and then you do this again, and after a finite number of steps, you end up with a solution of size 1. So those are multi-permutation solutions. So this is the name multi-permutation, well, comes from the idea that you are generalizing Lyubashenko permutation solutions, okay? And here you see the numbers of solutions, involutive solutions, and how many of them are not multi-permutation solutions. So for example, in size 4, you have 23 solutions up to isomorphism, and only 2 of them are not multi-permutation. In size, I don't know, you see, for example, the number of solutions that are not multi-permutation is always quite small. Almost all of them are multi-permutation, right? So, by the way, solutions of size 9 and 10 were recently computed in a collaboration with Agun and Martin Merev using constraint programming techniques. So we were using the combinatorics of the Yang-Baxter equation, but also this programming paradigm that it's some sort of very smart backtracking, okay? So the point is that if you see the list of solutions, you see that almost all of them are multi-permutation solution. So why? What can we say about that, right? Okay, this is a natural problem, right? So I would like to be able to construct solutions of size 11, and of course, I cannot do that because I don't have enough computer power. It seems to me that I need a new idea, okay? But going back to multi-permutation solutions, let me first show you an example. So here I have a solution of size 4, right? So here I have sigma 1 and sigma 2 are the identity. Sigma 3 is the transposition 3, 4. And sigma 4 is this product of 2 transpositions, right? So I have a solution of size 4. The retraction will have size 3. And it is the solution given by these permutations that I wrote there, okay? And then I can retract again, and then I get the trivial solution, the flip solution over a set of size 2, which again, after retraction, of course, produces the solution of only one element. This is how it works, the retraction of solutions, okay? This is a multi-permutation solution, a very concrete example of a multi-permutation solution. But the point is that almost all solutions are somehow like this one, okay? So, okay, so since you have like a lot of multi-permutation solutions, it is somehow natural to try to understand why. What is the reason, right? Why almost all of them are multi-permutation? And you can, of course, for example, try to understand this using the permutation group. The permutation group of a solution is by definition the group generated by the signals, okay? And there are several results. So for example, if the permutation group is cyclic, then you have a multi-permutation solution. This was proved by Rump quite a long time ago. If the permutation group of a solution is abelian, then you have a multi-permutation solution. This was proved by Sedó, Jesper, and Odninsky, and independently by Cameron and Gateva-Ivanova. And finally, if you have if your permutation group has abelian Sylow subgroups and has this a property, a technical property known as the Sylow tower property, then well, again, you will have a multi-permutation solution. Okay, so there are some results, group theoretical results, that somehow will produce only multi-permutation solutions. This might explain a little bit why you have so many multi-permutation solutions, right? At least if the size of the solution is quite small. But what I would like to mention is a different result, which was proved in collaboration with David Bachiller and Ferran Sedó. So what we did was to find a characterization of multi-permutation solutions in terms of left-ordered groups. So you say that a group G has a left order if you have a total ordering on G, which is compatible with left multiplication, right? Which means this formula that I wrote there. So this is quite well known in topology or in algebra. So for example, torsion-free abelian groups, free groups, and break groups are left orderable, okay? And what we did was to prove that if you have a non-degenerate finite involutive solution, then this will be a multi-permutation solution if and only if the structure group of the solution is left orderable, okay? So one implication was known from maybe 2004, I think, was proved by Jesper and Odninsky and independently by Shuraki. But the other one, which is the one that we proved, well, this was not known, okay? And this is quite interesting because you can use this to study multi-permutation solutions. Let me show you how. So with Victoria Levet, what we did was to find a new characterization of multi-permutation solutions using diffuse groups. I will not give you the definition of diffuse groups, but I will explain you how they appear, okay? Which I think it is even more interesting because the definition is quite technical, but not the idea behind it. So the theorem that we proved with Victoria is that if you have a finite involutive non-degenerate solution, then this solution is going to be multi-permutation if and only if the structure group is diffuse. And as a corollary, you can get a result similar to these group theoretical results that I mentioned before, right? So as a corollary with my student Emiliano Acri and Rafal Lutovsky, we proved that if you have a finite non-degenerate involutive solution in such a way that the permutation, all Sylow subgroups of the permutation group are cyclic, then you have a multi-permutation solution. So this was not covered in the list of theorems that I gave you before, right? But this is somehow an easy consequence of this result that we proved with Victoria. Okay, let me explain what diffuse groups are, okay? So diffuse groups appear in connection with this famous Kaplansky problem. So this is the unit problem. So take any torsion-free group G and consider the group algebra, complex group algebra of G. So the question is whether this has only trivial units or not. So what does it mean, a trivial unit? Well, a trivial unit is an element of the form lambda times G, where lambda is a non-zero complex number and G is just an element of the group. This is an open problem. It is not, nobody knows if this is true or not, okay? But what we do know is the following. So Kaplanski question has an affirmative solution if G is abelian, right? So torsion-free abelian. So if you go and read the proof, then you realize that you don't really need an abelian group, right? You can generalize this a little bit, and you can just, I mean, the proof essentially tells you that, well, Kaplanski question will have an affirmative solution if G admits a left ordering, right? So you are not using an abelian group. What you are using is the existence of a left order. That's nice. But if you go again to this proof and you go even further, then you can generalize this. So you can prove that Kaplanski question will have an affirmative solution if G has a super crazy property known as the unique product property. So what you are using is not that G is abelian or that G has a left ordering, but that G has the unique product property, a very technical property which is quite hard to check. Let me show you which is that. So a group G has the unique product property if for all finite non-empty subsets A and B of G, there exists an element X in G that can be written uniquely as something of A times something of B. But as you can imagine, checking this condition is really hard. I mean, it's almost impossible. This is where diffuse group appear, right? Because in some sense, so the definition of diffuse groups are groups that have the unique product property, right? And the definition involves some actions of the group, some action of the group, right? I will not give you the definition, the precise definition, because I don't want to, it's rather technical and I don't want to go into too many annoying details, but I just want to tell you that diffuse groups appear somehow naturally when you want to have a nice way of checking the unique product property using group actions, okay? It's very geometrical, this notion. And of course, then you have a new question, right? Diffuse group have the unique product property, but nobody knows if these two notions are equivalent or not, okay? This is a new problem that you have here. So here it means that I have a natural question, right? So I have a solution, an involutive solution, and the question is when the structure group of a solution has the unique product property. And here I have a concrete example that appears in this paper of Jesper and Odninsky, also in the book Noetherian semigroup algebras of Jesper and Odninsky. So you take a solution of size 4 given by all these permutations that I have there. This is an example of a solution that it cannot be retracted. So this is an irretractable solution, right? One of these two solutions that you have with this property. So then you can, of course, define the structure group, which is the group given by four generators and those relations. And you can check that this group does not have the unique product property. This was done by Jesper and Odninsky. What they did, the proof that they found is quite hard, for me at least. Here I have I think an easier proof. So in the theory of groups with unique product property, you find the promise law group, right? Which is a famous group that you might find, which is an example of a group that does not have the unique product property. And promise law in this paper used this funny set that I wrote there, S. So what I did here is just to use promise law set and an explicit realization of the promise law set inside the group G, the structure group of my solution, okay? So you can check indeed that with this set, well, you don't have the unique product property, okay? But okay, maybe you say, how can you do that? Because this is a group with a finite presentation, but how can you indeed check the two elements represent the same group, right? The same group element, because I mean, this is kind of hard because it is a group with a finite presentation, but you don't know how to compare elements, right? In general, this is very hard to do. But indeed it is not, because of the theorem of Etinghoff, Schedler, and Soloviev. So the existence of a brace structure can be reformulated into the existence of a faithful linear representation of your finite solution. So if you have a finite involutive non-degenerate solution of size n, then the structure group of the solution can be embedded. You have an injective group homomorphism into integer matrices of size n plus 1, right? And this is the explicit faithful representation for the solution, for the solution that considered by Jesper and Odninsky, right? And so checking that two elements are the same or not is very easy, right? Because you have matrices, so you can do this in a very, very easy way and very efficient way. But of course, the point is, can I do this for all solutions, all the solutions that I have in my database? Well, kind of, but not really. So the trick works for almost all of my solutions, but not all of them. I have some open cases. So I have some solutions where my trick, my set S, is not good enough to prove that, that I have the unique product property or not, okay? And so these solutions are quite good candidates for answering this question about the equivalence notion. So if diffuse groups, if unique product groups are diffuse or not, right? So it's not only that I don't know whether in general the structure group of a solution has the unique product property, but also I know, I mean, these are very good candidates to answer that question, right? So I have a very explicit group, which is not diffuse because, well, my solution is not multi-permutation. This is a consequence of the theorem that Victoria and I proved. But I don't know whether this this group has the unique product property or not. And it is quite interesting because it is very explicit, right? I have a group, I have a bunch of matrices, and I would like to check whether this group has the unique product property or not. Okay, so this is the problem, right? The very natural problem. So if I have an infinite involutive non-degenerate solution, when the structure group has the unique product property. And recall that, well, I have this faithful linear representation. I can just replace my group by a group of integer matrices, which of course is quite good for calculations. Very good. So this thing of having multi-permutation solutions is quite rich, not only because you can use group theory, you can also use ring theory. I will just mention this in a very quickly way. So if you have an involutive non-degenerate finite solution, then you can prove that your solution is going to be multi-permutation if and only if the brace that you have over the structure group is, say, nilpotent, right? Nilpotent here is a little bit sloppy. The right notion is right nilpotent, okay? So because you remember that a brace is somehow something like a ring, but you have this sort of funny distributivity condition, right? So when you want to consider nilpotency over these objects, well, you need to make a difference between right nilpotent and left nilpotent. And it turns out that the notion of right nilpotency is the one that corresponds to multi-permutation solutions. And well, this is very well studied. And so the connection between multi-permutation solutions and right nilpotency of braces is based on the works of Sedó, Jesper, Odninsky, Gateva, Ivanova, Rum, Agata Smoktunovics, and many others, okay? It's quite interesting, but it is more ring theoretical. Let me mention one more problem before finishing, which is somehow different to all the other problems. It's more combinatorial, right? So the problem is like this. So I have a finite solution, finite non-degenerate solution, and I would like to compute the growth series of the structure group of the solution. Okay, so let me explain you what is this and why this problem might be interesting. So if you have a group, then pick a finite set of generators of your group. Then you consider the Cayley graph of the group or the pair Gx, which is the graph with vertices in the elements of G and edges here, right, in G cross X. So you can define, of course, the ball of radius n as this set, and you can compute, of course, the size of this, which is a finite set, right? So then you produce this formal series, right? So essentially, you take so the series of the coefficient of Tn is the size of this ball, okay? And you are going to say that the pair Gx has a rational growth if the series is a rational function. So it is a quotient of two polynomials, okay? This is something, these sort of objects are well known and studied in group theory, in geometrical group theory, I would say. The point is the following, right? If a very strong theorem of Benson states that if you have a virtually abelian group G, this means that G has a finite index subgroup that it is abelian, then Gx has a rational growth for all finite set of generators X. And the point is that if you have a finite solution, the structure group will always be virtually abelian. So you can apply Benson's theorem, right? So the structure group of a finite solution will have a rational growth. This is for sure. But the point is to compute the series, right? So the paper of Benson contains a paper in Invenciones. I think it is from the 80s or maybe the 90s. I don't remember. It contains an algorithm, but I was not able to implement this algorithm, right? So, but however, it might, it looks like it is doable somehow, right? It's that you can indeed compute the growth series of a solution. So the case of involutive solutions is quite easy. This is not hard. The hard case is the general solutions, arbitrary non-involutive solutions, right? This is quite, I don't know which is the combinatoric behind this problem, but it seems to me that it is quite challenging. I think that this is the last slide that I have. So that's it. Thank you.